Okay. Okay. Good afternoon, all. From few lectures, we are discussing related to the heat treatment of the steels. In that, we have completed annealing, then normalizing, then hardening heat treatment process, then tempering heat treatment process. And after that, we have discussed related to the concept of what is the meaning of retained austenite, what are the effects of retained austenite, and how to eliminate that retained austenite by using the different processes. Then after that, we have started the surface heat treatment processes. And from that surface heat treatment processes, we have completed the first type, that is the carburizing heat treatment process. And now in today's lecture, we are going to discuss related to the nitriding heat treatment process, nitriding and carbonitriding. Carburizing, nitriding, and carbonitriding. These three processes will come in the surface heat treatment processes in which we are changing the composition of that steel. Okay, we are changing the composition either by introducing carbon or nitrogen, or sometimes we can introduce both carbon and nitrogen to the steel. And after that, we will move towards the some surface heat treatment processes that we are going to conduct without changing the composition of the steel. In that, we are going to deal with the two types of the hardening processes, that is flame hardening and induction hardening. Okay, now we will discuss that one by one. uh, First, we will start with the nitriding heat treatment process. Now, this process will also consist of, we have seen our concept of heat treatment process. It consists of one heating cycle, then holding time, and after that we are going to perform one cooling cycle. Here also we are going to follow the same process. Just how this process is conducted, that I will explain, and I have highlighted here a few important points. Along with these points, you have to explain that procedure, how to conduct it. Okay, first I will explain the procedure. Now, nitriding process, how it is conducted. In nitriding process, that the steel component is taken on which you want to perform the nitriding process. Our aim of this process is to increase the hardness wear resistance of the steel. Okay, on the surface we are going to improve the hardness. Okay, we want to improve the hardness and wear resistance of the steel. Along with that, automatically cutting ability of that material will get improved. Now, how it is conducted? First, the steel component is taken, and that steel component is heated in the furnace. Okay, it is heated in the furnace, but while heating, this heating process is carried out in contact with a medium which will provide you the atomic nitrogen. Okay, here the compulsory condition is that you have to take one medium which will provide you atomic nitrogen. Atomic nitrogen means you will end up with the separate nitrogen atom. Okay, should not be N2 like this. Molecular nitrogen should not be there. You require atomic nitrogen like this in this process also. Atomic nitrogen. Okay, atomic nitrogen must be there, means a source you have to use which will provide you at the end. Suppose here ammonia source we have used, at the end it will provide you atomic nitrogen. If molecular nitrogen is there, then diffusion of that molecular nitrogen does not takes place into the steel. That's why we are using a source which will provide you atomic nitrogen. This is very important point here. Sometimes they may ask you in the objective questions, that is which kind of diffusion will occur during the nitriding process. Options will be like this. They will give you combined options, and two confusing options will be like this: atomic nitrogen and molecular nitrogen. So your answer should be atomic nitrogen diffusion is occurring in this nitriding process, and if molecular nitrogen is formed, it does not diffuses into the steel. Diffusion process does not takes place if molecular nitrogen is there. Okay, in this way, uh, now I will repeat it. uh, While performing the nitriding process, you have to take the steel component, and that steel component is heated in a furnace with a source which will provide you the atomic nitrogen. And the heating temperature range is about 500 to 550 degrees Celsius. 500 to 550 degrees Celsius. At this temperature range, you have to provide the heat, and at this temperature zone, we are going to keep the constant temperature for 24 to 72 hours. And after that, that component is taken out from the furnace and it is cooled. Okay, and it is cooled. You can use the water medium or you can go for the oil medium for the cooling, depending on the type of the steel. And at the end you will end up with the getting one nitrided case on the surface, and its hardness and wear resistance will get improved. So in this way nitriding heat treatment is completed. First is the heating along with the a source which will provide you atomic nitrogen, and heating is done at 500 to 550 degrees Celsius, and holding is done for 24 to 72 hours, and after that it is cooled. Okay, after that it is cooled. So this is the nitriding process, and at the end the case depth achieved by this nitriding process is very thin case depths you can achieve here. Okay, now very thin case depths can be achieved in this nitriding process from 0.25 to zero point 0.5 millimeter. Now, here, depending on the medium used, these nitriding processes are classified in two types. If you have used the liquid medium for performing the nitriding process, then that process will be termed as liquid nitriding. And for that liquid nitriding, the medium used will be this molten bath, or you can say that the salt bath of sodium cyanide, about 10%, and in this sodium cyanide, remaining amount will be of sodium carbonate and sodium chloride. Okay, if you have used this medium, this is the salt bath composition or salt bath mixture containing 10% sodium cyanide and remaining amount of sodium carbonate and sodium chloride. This medium is very similar to the carburizing. Only one change is here, that in the carburizing process, in liquid carburizing process, we are adding here some metals like strontium, like that. I will show you that slide for liquid carburizing. Okay, we are same mixture is there here, sodium cyanide, 10% sodium carbonate and sodium chloride. And in addition to this, we are using some alkaline salts like barium, or you can say that elements like barium, calcium, strontium. These elements, salts we are going to use in this liquid carburizing. These salts are not used in case of this nitriding process. Only salt bath mixture will be used containing 10% sodium cyanide and remaining amount of sodium carbonate and sodium chloride. And whenever you are using this liquid medium, that nitriding process will be considered as liquid nitriding. And when you are using the gaseous medium, that is the ammonia gas, to get the atomic nitrogen, then this process will be termed as gas nitriding. And that these two processes I have highlighted in the this slide, that is types of the nitriding processes. Okay, here two types of the nitriding processes are here depending on the medium used. If we are using the liquid medium, in this liquid medium we are going to use the mixture of salt baths will be there, and that 10% sodium cyanide will be there. This percentage is very important. When this percentage changes, then automatically you will end up with the change in this reaction also. Use this Padge, Pritam Padge, stop sharing your screen. Okay, this is disturbance. Whether my presentation is visible? Kindly provide reply.
Yes, sir.
Presentation is visible?
Yes, sir.
Okay, okay. Okay, I will continue then. Okay, depending on the medium used here, nitriding processes are classified into two types: liquid nitriding and gas nitriding. Whenever we are using the liquid medium, in this liquid medium, we are going to use the salt bath mixture. It's mixture of the salts in the liquid state, containing sodium cyanide 10%, and remaining amount will be of sodium carbonate and sodium chloride. Then whichever reaction is occurring here, this reaction will take place. This reaction will be same in the liquid carburizing also. Same reaction was there. That same reaction you can write here. And just what will happen here, this atomic nitrogen diffusion will occur in this nitriding case. Now question will arise here, why carbon does not diffuses during the nitriding process? Why only nitrogen will diffuse here? So answer for this is, we have used the lower temperature, that is the nitriding temperature is in the range of 500 to 550 degrees Celsius. Okay, nitriding temperature is at in the range 500 to 550 degrees Celsius, and at that temperature in the steel only ferrite phase is there, and in that ferrite phase diffusion of carbon will occur in very smaller amount. Okay, very smaller amount. That's why the highest diffusion will be of nitrogen only, or carbon diffusion does not take place at that temperature range. And whenever we are using higher temperature range, that is above 700 or above 800 or 900, at that time diffusion of carbon will take place, as there will be presence of austenite phase. Okay, so this is the reason why we are using same medium, but diffusion of only nitrogen takes place, because nitriding process we have selected the lower temperature zone, and at that temperature zone austenite phase is not present there. That's why diffusion of carbon does not take place. Only diffusion of nitrogen will occur here. Okay, this reaction you have to write. From these two reactions, only one reaction is sufficient. You can write either this one or this one. First reaction compulsory you have to write. This is the sodium cyanide. It combines with the oxygen and it will form the sodium cyanate. This NaCNO is sodium cyanate. This is sodium cyanide. NaCN is sodium cyanide, and this is sodium cyanate. And again, this sodium cyanate decomposes, and it will provide you sodium cyanide, then sodium carbonate, carbon, and nitrogen. Nitrogen. This is the atomic nitrogen, and this atomic nitrogen will get diffused in the steel. And how it will improve the hardness of that material? Okay, now hardness. How the hardness is improved? That is our purpose. Now this nitrogen, atomic nitrogen, which is diffused into the steel, it will react with the iron present in that steel. Okay, it will react with the iron present in that steel, and it will form the iron nitride. And this iron nitride is very hard in nature. Due to that, the hardness of that steel will get improved due to formation of that iron nitride. Or sometimes it will result in the, if other alloying elements are present in that steel, it will form the respective nitrides. Suppose aluminum is there, aluminum, tungsten, vanadium, then that respective elements nitrides will be formed, and that nitrides will be very hard in nature. That's why hardness will get improved. Okay, so in this way, due to the diffusion of that atomic nitrogen, formation of iron nitride and respective nitrides of form due to the reaction with the other alloying elements with the nitrogen, and hardness of that steel will get improved. And the second type will be gas nitriding. In gas nitriding process, here in the gas nitriding process, the medium used is the ammonia gas. Okay, by dissociation of the ammonia gas, atomic nitrogen will be formed, and this atomic nitrogen will get diffused in the steel, and that atomic nitrogen combines with the iron to form iron nitride and other alloying elements present in that steel to form respective nitrides, and due to formation of these respective nitrides, it will result in the improved hardness on the surface of that steel. So in this way, this nitriding process is conducted, and depending on the medium used, there are two types of the nitriding: liquid nitriding and gas nitriding. Okay. Now here, this process, in this process nitriding, one question will be there. Lots of times they have asked this question. Instead of asking the nitriding process, they have asked this question. Means here some explanation you have to provide. They will ask you this question combinedly. This is a very important part. The first question will be, why only alloy steels are suitable for nitriding? And next question is, plain carbon steels cannot be nitrided. Okay. In this, you have to provide a certain reasoning or conceptual answering should be there in this. Before going for the reasoning, first kindly note down the important points for this nitriding. Just mention the types, just write down the mediums and its reaction. Please write down the reactions. I will wait for 2 minutes here, and after that I will explain you that why only alloy steels are used for nitriding process, or these are suitable for nitriding process. What exactly occurs there in the nitriding process for alloy steel and plain carbon steel, that you have to write. Answer is very simple. uh, it will be in the two, just two reasons will be there, one for that plain carbon steel and one for that alloy steels. Okay, that you have to write. Please write down the reactions. I will wait for 1 minute, 1 or 2 minutes here. Please write down the reactions, type of the nitriding and the reactions occurring there, so that you will find it familiar while you will start your self study. Okay, I'll wait for a few minutes. If you have completed, can I move towards the next slide? Please give me reply.
Yes, sir.
Okay. If you are not understanding any point, or if you are finding it difficult, you can ask questions here itself. If you are having any questions, please ask me. Okay, we will move towards the this important point, that is why only alloy steels are suitable for nitriding, and why plain carbon steels cannot be nitrided. So I will start with the second question, that is why the plain carbon steels cannot be nitrided. Okay, now we can do the nitriding process here on the plain carbon steel, but we are not using it for doing it. There are certain reasons. When we perform the nitriding process on the plain carbon steel, what will happen uh, during the nitriding process? What will happen? Atomic nitrogen will get diffused into the steel, and that atomic nitrogen will combine with the iron present in that steel, and it will form the iron nitride. Okay, and now in plain carbon steel, only formation of this iron nitride will take place. Okay, as there are no other alloying elements, only iron nitrides will be formed, and this iron nitride will form a continuous layer. It will form a continuous layer on the surface. Okay, it will form a continuous layer on the surface of iron nitride. And when you want to observe its microstructure, okay, before observing the microstructure under the microscope, you have to do the apply some agent on it. Okay, so that its microstructure, its grain boundaries will get revealed. For that you have to apply some agents, but this white layer is not visible, or you cannot use any agent so that it will get revealed. Okay, it does not get revealed under any microscope. You cannot do the etching process on it. Due to that, what will happen here, when you observe this plain carbon steel after completing the nitriding process, you will be able to see only a white layer, continuous white layer will be there. And due to that iron nitride white layer, this iron nitride white layer is very hard and brittle in nature. Whenever you are using it, that particular nitrided component, plain carbon steel nitrided component in actual practice, then it will get break, some cracks will get formed due to the brittle nature of that iron nitride. Okay, due to the brittle nature of that iron nitride. That's why we are not doing the nitriding process on plain carbon steel. Okay, simple answer is the in this way. Just you have to write this: whenever you perform the nitriding process on plain carbon steel, nitrogen will get diffused into plain carbon steel, and it combines with the iron present in that steel and forms iron nitride. And as there is no other alloying element, only iron nitride will be formed, and it forms a continuous layer, and which appears white in color under the microscope. And this white layer formed of iron nitride, it is very hard and extremely brittle in nature. And when you use this component in actual practice, it will get cracked. It will get cracked during the actual service. That's why plain carbon steels cannot be nitrided. This will be your first reason. This is the reason for why the plain carbon steels cannot be nitrided. Okay, only formation of iron nitride will be there, and continuous white layer will be formed, which is very brittle in nature. Now we will move towards the alloy steels. What exactly happens during the nitriding of alloy steels? Now, in this case of nitriding of the alloy steels, when the diffusion of nitrogen takes place, that nitrogen will combine with the iron present in that steel, alloy steel. Nitrogen and other alloying elements will be there. Then that nitrogen will combine with the iron, and it will form iron nitride. And that nitrogen also combines with other alloying elements present in that steel. Suppose there may be chromium, molybdenum, vanadium, manganese, tungsten. Number of alloying elements may be there. Then that nitrogen will combine with that alloying elements, and it will form its respective alloy nitrides. Okay, that alloy nitrides will be formed depending on the alloying elements. Iron nitride formation will also take place, and along with that other alloy nitrides will be formed. And the nit- iron nitride which is formed, it will present only on the surface in the form of a white layer. Okay, same process is occurring in the plain carbon steel. Iron nitride white layer will be formed. In alloy steels also, alloy nitrides white layer will be formed on the surface, but nitrogen is also combining with other alloying elements present in the steel to form alloy nitrides. And at the end you will get other than surface, in the remaining portion there will be alloy nitrides will be present in the form of a needle shape along with the ferrite phase. At the room temperature you will get the structure like this in the alloy steels. On the surface, iron nitride white layer will be there, and after the surface in the remaining portion alloy nitrides will be there along with the ferrite. Due to that, what will happen, the remaining portion other than that surface, remaining portion will provide you hardness along with the toughness also. It will provide you better hardness along with the toughness. Only one thin layer will be formed, one thin white layer will be there of iron nitride, and that can be removed, that can be removed by performing one grinding or lapping operation. That layer can be removed. So only alloy steels are suitable for nitriding. Okay, this is the reason why only alloy steels are suitable for nitriding. In alloy steels also iron nitride layer is formed, but it will remain only at the surface, and in the remaining portion other alloy nitrides will be formed by combination of nitrogen and other alloying elements. And at the room temperature, uh, phases will be like this: ferrite will be there and these alloy nitrides will be there in the form of a needle like structure will be there of these alloy nitrides. Due to that, they will provide you the hardness, and due to presence of ferrite they will provide you the toughness also. And when you observe under the microscope, that iron nitride will be observed as a white layer, and the remaining phases will be observed in the form of a dark layer. Remaining phases will be observed as a dark layer, means that other alloy nitrides will be, you can observe them in the form of dark phases. In this way, due to formation of that alloy nitrides, it will provide you the required hardness and toughness. Hence alloy steels are suitable for nitriding. Whichever iron nitride is formed, that will present only on the surface in the form of a thin layer, which can be removed by one grinding operation. So this is the reason why only alloy steels are suitable for nitriding, and why that plain carbon steels cannot be nitrided. Okay, have you understood the reason, or I have to explain it again? Please answer me. This is very
Yes,
important question. Okay, okay. Uh, any other student? Kindly provide replies. Uh, Milind Jagdale,
yes, sir.
roll number 34. Okay, okay. Okay, this is very important questions. Maximum times they in examination they are asking this reasoning only. Okay, they will ask you this reasoning, or sometimes in competitive examination also they may ask you this question. Okay, okay. After finishing this point, we will move towards some advantages and disadvantages of the nitriding process. Okay, now there are certain advantages in the nitriding process. The first advantage is will be like this: it does not require a hardening treatment. Okay, as in the carburizing process, after completing the carburizing we are performing one more hardening process. That is one more time we are heating the component, then holding it and again cooling it. Okay, this is not required in case of nitriding. It does not require any further heat treatment process, as during this process distortion is minimum. And this can be this nitriding process can be applied through the parts where close dimensional accuracy or close dimensional tolerances are required, like your precision gears, then boring bars, then camshafts, crankshaft, cylinder liners, etc., or forming dies. You can write this component's name in the application also. So these are the advantages. It does not require, nitriding process does not require any further hardening or further heat treatment process is not required. Then The next point will be nitrided components shows you better corrosion resistance and better fatigue life. Okay, why they are providing the better corrosion resistance? Because on these layers which are formed, there will be presence of some high residual compressive stresses will be there. Some compressive stresses will be there on the whichever surface layers we are forming here. That nitrided layers will be there. Nitride layers will be there of iron nitride. You can say that alloy nitrides layers will be there. In that, some compressive stresses will be there. Due to that, it will provide you better fatigue life. Then it is having better corrosion resistance. Then better galling resistance or seizing resistance is very high. Or in short, you can say that they will provide you better bearing properties. Then next is because of the non-metallic nature of the nitrides, that nitride surface has very less coefficient of friction. And the last advantage will be like this: the nitrided cases, they will provide you higher corrosion resistance. Sorry, here corrosion resistance I have already mentioned. Here you can write the hardness. Okay, instead of this corrosion resistance, nitrided cases will provide you higher hardness. Okay, hardness is there. That point I have missed, I think. Corrosion I have already taken here. Here you have to add that nitrided cases shows you higher hardness than carburized and hardened components. Okay, if you take the same kind of steel and if you perform carburizing, then hardening and nitriding process, then you will find that that nitrided component will provide you the better hardness values. Okay, better hardness will be there. So these are some advantages. Then after seeing these advantages, we will move towards some disadvantages of this nitriding process. Now already we have studied the in the reasoning that only plain carbons, only alloy steels can be nitrided, plain carbon steels cannot be nitrided. That is the disadvantage of this process. Okay, you can write that point in the disadvantages. That is only plain carbon, only alloy steels can be nitrided, plain carbon steels cannot be nitrided. Only alloy steels can be nitrided. And the alloy steels which can be nitrided are termed as nitralloys. These are termed as nitralloys, and these are very costly. These nitralloys are very costly. Okay, that is another disadvantage. Then usually by this nitriding, we will end up with the very thin case depth. Whichever case depth is achieved, it is very thin. Up to 0.5 mm only we can achieve the case depth. Okay, that is another disadvantage. Then the next disadvantage is, as we have discussed in the reasoning of that why only alloy steels can be nitrided, that one thin layer, white layer of iron nitride will be formed, that you have to remove. Okay, the thin white layer will be always there after the nitriding process, which requires some grinding operation or lapping operation, which is difficult and little bit costly. This is one more disadvantage: formation of a thin white layer of iron nitride on the surface of that steel component, and which requires some grinding operation. So it will take some time, and it will also take some cost for removing that. That you can write adding the disadvantage of this process. Then the last disadvantage is, as you can use this as an advantage as well as you can say that this is also a disadvantage. That is, no further heat treatment can be done after nitriding. You can say that this is an advantage. And why this is, I have added in the disadvantage also, because if suppose at the center or core, just here we are changing the properties on the surface, surface will become hard, but the core properties cannot be changed. That's why whichever core properties are required in that component, that you have to adjust before performing the nitriding process. Okay, that I have mentioned here, the core properties should be adjusted before the components subjected to the nitriding process. Before performing the nitriding, you have to adjust the core properties only, because after nitriding you cannot perform any further heat treatment process. Okay, so these are the some advantages, 4 to 5 advantages, and four disadvantages are there. If you have understood that full nitriding process, you can summarize these points. Okay, so after this nitriding process, okay, in this nitriding process you have seen, what we have learned. First, you have to write the purpose. What is the purpose? We want to improve the hardness and wear resistance of the steel, and along with that some, you can say that in some kind of steel it will improve the cutting ability also. Main purpose is to improve the hardness and wear resistance of the steel. That is the purpose. Then procedure you have to mention, and after the process you have to mention the types, and after that types you can write advantages, disadvantages, and some applications. And if they have asked this question, or you can also mention it in short way, why only alloy steels can be are suitable for nitriding, and why we cannot perform, or why we are not performing nitriding process on plain carbon steels. Okay, so these are the points included in the nitriding process. Then after this nitriding, the next type is carbonitriding. Okay, I'll wait for 1 minute here. If you are having any questions related to the nitriding, please put that in the chat box, or you can ask me directly also. I'll wait for 2 minutes. If you are having any queries, please ask me. Okay, this carbonitriding will be just a combination of carburizing and nitriding process. This is just the combination. Okay, you have to just do the combination here. That's why, if you have understood carburizing and nitriding easily, you will be able to write the carbonitriding process. Just you have to change the temperature range, and you have to do the combination of the mediums. Okay, I will wait for 2 minutes. If you are having any query, please ask me. Okay, if you are not having any query, we will move towards this next type of the heat treatment process. Okay, in the carbonitriding process, just you have to remember this. This is the combination of carburizing and nitriding heat treatment process. Means in carburizing we are introducing the carbon into the steel. In nitriding we are introducing the nitrogen into steel. But in carbonitriding we are introducing both carbon and nitrogen into the steel. So why this? Why we are performing now, instead of performing only nitriding, we are going for carbonitriding. So reason behind this is that it is observed that whenever some amount of more amount of carbon is present in the nitrided components, it will show you the better life, or you can say that better properties, better service life, and better properties will be there. Whenever more amount of carbon is there in the nitrided components or nitrided cases, it will provide you the better service life and better properties That's why this concept of introducing carbon and nitrogen both in the steel is introduced, and this method is termed as the carbonitriding. Now, how this process is conducted? Now, in the same way as we have conducted the nitriding and carbonitriding process, this process will also conducted, but just we are going to change the temperature zone and the mediums used while performing the heating. Now, in the carbonitriding process, we are taking that steel component. We are in the carbonitriding process. The steel component is taken, and that steel component is heated. It is heated at 750 to 850 degrees Celsius. Okay, 750 degrees Celsius to 850 degrees Celsius. Generally, this temperature from your iron carbide equilibrium diagram, it lies in the above A1, just above A1, and it will be lesser than the A3 temperature. It is lesser than A3 temperature, but just above A1 temperature, and generally it will come in between 750 to 850 degrees Celsius, and we are heating this component in a medium which will provide you carbon and nitrogen both. Okay, it will provide you carbon and nitrogen both. Now, how you are getting the carbon and nitrogen both? Here we are either using the liquid medium, which consists of salt bath mixture of sodium cyanide with 20 to 30% sodium cyanide will be there, and remaining amount will be of sodium carbonate and sodium chloride. Same mixture we have used in the nitriding, but here what we have changed is amount of sodium cyanide. The sodium cyanide is the source of carbon and nitrogen. This is providing you the carbon and nitrogen. The amount of this we have increased here. And if you are using the gaseous medium, here we are using uh, gases like methane, ethane, propane, butane, along with 5 to 10% ammonia gas. Okay. From this ammonia gas, we are going to get the nitrogen, and from this methane, ethane, propane, or butane, whichever alkane material you have used, from that we are going to get the carbon. Carbon we will get from this, and nitrogen we will get from this dissociation of this ammonia gas. Okay. In this way, we can go for either liquid medium or for gaseous medium. And depending on the medium used, this carbonitriding process again has two types that I will discuss in the later half of this lecture. Just you have to understand that while performing this carbonitriding process, the steel component is taken and it is heated in the range 750 to 850 degrees Celsius in the in presence of the medium which will provide you carbon and nitrogen both. For example, you can write these two mediums, and this process and at that temperature that component is held for less than 1 hour, approximately 1 hour, and after that it is cooled in the oil or in the water medium. Okay, the quenching process will be performed by using the water or oil medium. Okay, so this is, and at the end you will end up with the formation, end up with the carbonitriding process, and the case depth achieved here, very smaller case depth can be, or thin case depth can be achieved from 0.075 millimeter to 0.25 millimeter, and this is achieved with very small time, that is less than 1 hour. You can complete this process of carbonitriding. Okay, so in this way, this carbonitriding process is conducted, and now depending on the medium used, this carbonitriding process is classified in two types. If you have used the molten salt bath mixture of sodium cyanide containing 20 to 30% sodium cyanide will be there, and remaining amount of sodium carbonate and sodium chloride will be there, then this carbonitriding process will be termed as liquid carbonitriding, or this process is also known as cyaniding, or this process is also known as cyanide hardening. Okay, here you can write the same reaction. You have to write the reaction here also. This reaction you can mention there. The same reaction will occur, and carbon and nitrogen you will get here. And now the question will arise like this: how the diffusion of carbon and nitrogen both will take place? Now, the same reaction you can write there, and carbon and nitrogen will be formed. As here we have used the temperature 750 to 850 degrees Celsius. In that range, ferrite and austenite will be there. Whichever nitrogen is there, it will get dissolved. Okay, whichever nitrogen is there, it will get dissolved or it will get added in that ferrite. And whichever carbon is there, this carbon will get dissolved or added in the austenite, as austenite will be there above 750 degrees Celsius. In case of nitriding, we have used temperature maximum up to 550. Only ferrite will be there. That's why carbon does not diffuses there. But in case of carbonitriding, we have used a higher temperature zone. That's why there will be presence of ferrite and austenite will be there. Carbon will get diffused in the austenite and nitrogen will get diffused in the ferrite. In this way, diffusion of both carbon and nitrogen will occur, and at the end we are doing the cooling in the oil or water. Due to this, what will happen? Whichever carbon is dissolved, that it will get transformed from austenite phase to the martensite phase, and it will improve the hardness of that component. It will improve the hardness of that component. Okay. Now, if you used the gaseous medium like methane, methane is nothing but CH4, or ethane is nothing but C2H6, along with 5 to 10% amount of ammonia gas. This ammonia gas, it will give you atomic nitrogen, and this methane or ethane, it will give you carbon. Carbon, it will get diffused in the austenite. This nitrogen will get diffused into the ferrite, and at the end, when you quench it in the water or oil, this austenite or carbon present in the form of austenite, it will get transformed to martensite, which results in the improved hardness, which results in the improved hardness of that component. Okay. Now, this gas carbonitriding is also known as dry cyaniding, or it is also known as gas cyaniding, or it is also known as nitrocarburizing, or it is also known as nicarbing process. Okay, different names are there. I try to identify all names. They may ask you in examination, they may provide you any name. Means they will ask you to explain the nicarbing process. Then you will get confused. This is out of syllabus question, but this is the other name for the same process depending on the medium used. Okay, liquid carbonitriding is also known as cyaniding and cyanide hardening, and gas carbonitriding is known as dry cyaniding or gas cyaniding or nitrocarburizing or nicarbing process. Okay, and these are the mediums used. And for gas carbonitriding, and this is the liquid medium used for liquid carbonitriding. Also, you have to mention the reactions which are occurring here. You can write the same reactions which you have used for the nitriding. Okay, same reactions you have to write. Depending on the higher temperature zone, diffusion of nitrogen and carbon both will take place here. Okay, so this is the carbonitriding process along with its types, how it is performed, how much temperature zone medium used, how much time is required, and how much test depth is achieved. Then which medium is used for quenching here, that you have to mention here, oil or water medium. The types of the carbonitriding depending on the medium used, that you have to mention here, and you have to write reactions also here. The same reactions you can write. Okay, these are the surface heat treatment processes. It is carburizing, nitriding, and carbonitriding, in which we are changing the composition of steel. Now there are some surface heat treatment processes which we are conducting without changing the composition of steel, and in that we are going to discuss two types, that is the flame hardening and induction hardening process. Okay, next will be the flame hardening. uh, can I start this flame hardening, or can we continue this in the next lecture? Please provide reply. Can we continue with the flame hardening, or we can see this in the next lecture also? If you are finding it means that lecture is extending or it is becoming too heavy to understand, then we can take this in the next lecture also. Please put that in the chat box. Okay, no problem. Okay, okay, we will continue this in the next lecture. Okay, no problem. In the next lecture uh, we are going to discuss the process surface heat treatment processes which are conducted without changing the composition of steel. We in that flame hardening and induction hardening will be there. We will discuss that in the next lecture. In today's lecture we have completed the nitriding process, what we have discussed, nitriding process, how it is conducted, purpose, then its procedure, then its types, along with the reactions, then why nitriding process is conducted, or only alloy steels are suitable for nitriding, why plain carbon steels cannot be nitrided, and some advantages, disadvantages of the nitriding process. And then after that we discussed related to the carbonitriding, what is the purpose of carbonitriding, then what is the procedure or how it is conducted, then different types of the carbonitriding process depending on the mediums used. Okay, in this way we have completed this part, this half part of the surface heat treatment processes. Only two types are remaining there, flame hardening and induction hardening, that we will continue in the next lecture. Only 3 points are remain from this chapter: flame hardening, induction hardening, and one more point regarding the hardenability. Means 3 points are left from this chapter. If possible, I will complete all these 3 points in the tomorrow's lecture. Okay, means we will end this chapter maximum, means at least it will require one lecture, or if possible I will convert that in the two lectures. Okay, so if you have understood all parts, I will stop here. Okay, if you are having any query you can ask me. If you are not having any query, I will stop here. Thank you.